If the aberration is there, then it will affect not only the trajectories but also the image size, shape, and of course the locations also that will change. Now, so far we were talking about particle trajectories. Now, there are two kinds of beam. One is, or two kinds of accelerators actually. One is called low current accelerators, where we get low currents at the output also, and other one are called high currents accelerators, and there are many applications where high currents are required. For example, for nuclear physics experiments, low currents are good enough because the cross sections could be high, or you would like to have a very clean data. While in many cases like accelerator driven systems, high currents are required because number of neutrons produced and hence the power generated is proportional to the current. Now, so the trajectory calculations in both the cases are totally different. The type of beam image you can get are totally different. For example, if you take a low current, then you can even you are required to track the particles, single particle. So you have to do a single particle trajectory calculation. While in the case of high current accelerators, that is no more true. So you have to do a different collective motion you have to take into, and you will see in later I have explained that in the high current accelerator, the particle make a sort of envelope. They move in the envelope, so you have to trace the envelope rather than the single particles. So in the case of low currents, you have to do the particle trajectory calculations. And system particularly through, particularly like accelerating tube. In the case of DC accelerators, accelerating tube is the most important part of it. And accelerating tubes have cylindrical symmetry, so that makes our life simple. Calculations can be simple, but you have to minimize the aberration by properly designing the accelerating tube shape as well as the voltage distribution. You will see in the following slides that not only the electrode shapes but also the voltage distribution which you are putting across the accelerating tube matters a lot in focusing the beam. So what ultimately you have to do is, if you want to design a proper system, then this accelerating tube has to be designed based on the ion trajectories. And for that, as we mentioned earlier, we did in the case of lens also, that you have to solve the equations of motion for the charged particle through the ion optical components. You have to do right from the ion source up to the target. Of course, in this case, the accelerating tube plays a most important role. Now, if you have, as in the case of DC accelerators, if you have a accelerating tube and particle is moving along the z-axis, then it will have the rotational symmetry, that means theta symmetry, and therefore the potential distribution. So the ion, ultimately we have to do the ion optics. So this ion optics, that means you have to follow the ion trajectories, you have to calculate the ion trajectories using the potential distribution. And so first it involved two steps. One is that you have to calculate the potential distribution, and using those potential distribution you have to calculate the trajectories. So if you have cylindrical symmetry accelerating tube, then the potential distribution is will have this Poisson's equation, and this is shown here, and Poisson's equation will give you the potential distribution. And here you can see on the right hand side, rho is the charge density, and I am considering the first case where the current is very low, and if that is the case, then this rho can be neglected. So you can put right hand side to equal to 0, and that is true only if the currents are very small. Otherwise, you have to solve this Poisson's equation. However, if the currents are low and space charges are not there, currents are small, then you can charge density negligible, and therefore you can solve potential distribution can be obtained not by you don't have to solve that equation. You can solve the Laplace equation by putting right hand side equal to 0. And in the coordinates where now I am cylindrical coordinates, where I am having r or theta and z. Z is the beam axis direction, and it is having a theta symmetry. Then this equation can be converted into like so. This is the equation we have to solve for getting the potential distribution large square. So what it effectively it amounts to, you can see that distribution means you have to, from the trajectories you have to calculate r, the position, and as a function of z, and this equation will give you the potential distribution, and then you have to solve the force equations using the potential distribution which you have got from the calculation by solving the Laplace equation. So these are the two equations you have to solve, and they can be in Cartesian coordinate, they can be, or they can be written as in even cylindrical coordinates, z and r and theta. So theta will not appear because at each theta the r will be same, and therefore you have to solve these two equations for ion optics calculations. So in the nutshell, it is beam optics involve calculation of r as a function of z, rz, in electrostatic field which you have calculated using either the Poisson's equation in the case for high current, or the Laplace equation when the current is very small. And as I mentioned earlier that in the case when the currents are pretty high, then this does not behave like a particle alone, it behaves like a collective of particles. And collective of particles, you will see later on that they do not behave individually, but they behave in a collective manner, and there is something called all the particles are contained in an ellipse rather than a point. So in the case of in this case, I have taken a very simple example of 2 million volt tandem accelerator built at BRC, and that is because these calculations were done, and based on the calculations the accelerator was built, and the actual measurements and the calculations were matched, and they matched very well. And of course we learned a lot from this. So I will be taking the examples of this case. In this case, you will see some of the conclusions were that when you do the calculations, then you have to take sufficient fringing fields. So calculations of potential distribution, V, which is a function now of R and Z with the theta symmetry, then shape of the electrodes, the direction of the electrodes, and the potential gradient, all are important. And fringing effects have to be accounted for, otherwise you will not get the correct results. And that is what we found it also. And of course then you have to, so these are the two things. And if anybody is interested in more details, they can see these references in this case. Now this is the first column section of the 2 MV tandem, which was built at BRC, and it worked for several years. And you can see this accelerating tube which we are talking about, it can have different shapes. As I said, the shape matters. And you can see that if the beam is going like this, then the electrode can either be straight, you can see this is straight here, separate by certain distance, or they can be inclined. They can be inclined, but this shape can be either towards input side or it can be towards output side. You will see the results are totally different. Now, in the case of our present case, this tandem accelerator, we took this based on the calculations and the actual measurements. We did all the measurements in both the cases. See, if you reverse it here, then this will be the geometry. If you put it like this, then this is the geometry. And then you will see that the results were totally different and the performance of the accelerator was totally different. Earlier, prior to these things, we found that in most of the literature, accelerating tubes were used like this. And it was found that the transmission was not very good. When we changed these electrodes like this, which is shown here, then the transmission increased remarkably. Now, these are the electrodes. These are stainless steel electrodes, and they are separated by glass insulators here, and which is rough. So, these electrodes, they are fixed voltage electrodes. You are only calculating the potential distribution in this region where the beam is going. So, let's say the beam is going in this way. Then you have to calculate the field distribution or the voltage distribution in this region, and then calculate the trajectories along this. And this was done, but these electrodes are applied. Now, there are two ways of applying. One is you can say see here this is a part of the accelerating this beam line, which is grounded, zero potential. So you apply 0, you can apply 0, 40, 80, like this is called constant gradient. That means the voltage difference between all of them is equal, and let's say it is 40 or 50 or whatever. Other cases that you can apply 0 here, and then it is 10, 20, 40, like this. That means in first few sections you apply some variable gradient. And you will find that there is a remarkable difference. You can see that in the case of variable gradient, this is the constant gradient and this is variable gradient. And you can see that voltage distribution is here. And one thing you can notice here, that the fringing field goes at least 4 to 5 times of the aperture of this accelerating tube. So you have to calculate this potential distribution up to quite a large distance, because this is going to make such a great difference. You can see here the ion trajectories calculated for this potential distribution. Here you can see that it's not constant gradient. It is 0, 10, 20, 40, like this. It is going on. So first few electrodes, the gradient is lower, and then it is constant. And then after that it does not matter, because the velocity or the speed of the particle has already increased, and therefore focusing effect will not be too much disturbed will not be affected by this voltage distribution. So you can see that how nicely we get this. This is a tandem accelerator. So there is in the center there is a stripper where the negative ions get converted to positive. So in this region it is positive. Here this is a stripper. Here is stripper. So you can see that how nicely the trajectories are passing through a very small region of the stripper. While if you take this, right from the beginning a constant gradient, that means it is 0, it is 40, 80, 120, like this. That means 40 kV per section. Then for the same parameter, for same input parameters, you can see that in some cases the trajectories are diverging, and therefore they are not passing through the stripper, and those ions will be lost. In fact, even in this case, which is passing through that, you will find that this by the time they reach the second accelerating tube, target is like this. Experimental target is there, but the beam will be passing through some other place, and it will be completely missing the target, and experiment will not be. So you can see that if you compare this is the ion trajectory for corresponding to this variable gradient, and this is ion trajectory corresponding to constant. And you can see a remarkable difference between these two. And this is far. So you can see that two effects are there, which I talked about. One is the shape is mattering. Second is your fringing field here, which you have accurately calculated. We calculated up to a distance where the voltage becomes very small, really negligible. Till that time we calculate. Of course, it will take more computer time, but it gives more accurate. However, so one is shape, this shape, then gradient, and then the fringing field. All three are making huge effect. You will see in the later one, the calculations are not properly done. The transmission of the beam lowers down considerably. Now, I mentioned there that the shape as well as the size of the beam at the output on the target will really matter based on the aberrations. You can see that here I am injecting all the parallel beams with this, and with that field distribution, this is for the first one, which is a variable, and here it is for constant one. And you can see here that in the case of variable gradient case, the focal length as a function of r is always rising. With r, if it is focal length is increasing always, it is called negative spherical aberrations. However, in the case of this, where it is a constant gradient, first it becomes negative, but then as the particle moves away from the optical axis, it changes the sign of the aberration, and it becomes positive here, which is not a good thing. And this was the conclusion we have drawn from this. And you should have only one type of aberration, whether it is negative or positive, because correcting that becomes simple. So these were the trajectories based on. And of course, the calculations we did for entire accelerator involving both the accelerating tubes, low energy as well as with the common dome, common high voltage. And you can see that if you inject a heavy particle, like for example, this calculation is for mass is equal to 40, and these calculations were done for tandem accelerator, which requires injection of negative ion. So is arbitrarily A is equal to 40 I have taken, and if you calculate the trajectory throughout, then as the charge state increases, energy increases, and then you will see that the beam dimension keeps coming down, because you know that once the particle has moved, and if the charge state is high, the force will be stronger and it will be focused more and more, and therefore the beam size on the target will become small, and that is what is shown here. So all this depends on potential distribution, that is the shape and the direction of the electrode. This was a conclusion, and this was almost done, not very regularly done in the literature, and therefore this was a sort of good finding of this study which we did.